Hello, welcome. In this video, we are going to give the definition of a metrizable space. We define a metrizable space as a topological space X such that the topology of X is generated by some metric on X. So, a topological space X is metrizable if there exists a metric on X that can generate the topology of X. If there exists, the space X is a topological the topological space X is a metrizable space if there exists a metric on X that can generate the topology of X. And here we are going to see that the property of being metrizable is a topological property. What does it mean? It means let X be a topological space which is metrizable, and Y be another topological space which is topologically equivalent to X. Then Y will also be a metrizable space. That means we can find a metric on Y such that the topology on Y can be generated by that metric. So, see the statement. The property of being metrizable space is a topological property. In order to prove this result, first we consider a topological space XD in which D is a metric. See, here D is a, suppose D is a metric which is defined on the topological space X, and there is a topology on X. Moreover, the topology on X is determined by or is generated by the metric D. As the second point, we consider a space, another topological space Y, such that the space Y is topologically equivalent to X, or there exists a homeomorphism from X to the second space Y. So these are the facts we are using. These are the important concepts that we are using as true in the entire proof of the statement. Okay, now it is given, it is shown here that F is defined from X to Y is a homeomorphism. We consider, or we suppose that F is a homeomorphism which is defined from X to Y. And what kind of space is X? X is a metrizable space. That means there is a metric D on X. Moreover, the topology on X is generated by that metric. And we can divide the proof of the result into two sections. In the first section, we will show that there exists a metric on the space Y. That's the first part. And the second part we will show that the topology on Y can be generated by that metric defined. So we proceed to define the metric on the space Y. The metric is defined as D prime. So let D prime be the metric which is defined on the space Y, and Y1 and Y2 are two members of the space Y. Then D prime of Y1, Y2, and we give the definition of the second metric. D prime, it is defined as D prime of Y1, Y2, where Y1 and Y2 are two elements of the space Y. So D prime of Y1, Y2 will be defined equal to D is the metric which is available on X. The D of F inverse of Y1 and F inverse of Y2. See, F inverse of Y1 and F inverse of Y2 are two elements in X. So this is meaningful. So here we measure the distance between the points F inverse of Y1 and F inverse of Y2. And that distance will be a positive quantity, and this quantity will be used as the value of the metric D prime of Y1, Y2. Next we proceed to show that this definition is meaningful and D prime is actually a metric on the space Y. For this, let's first take the statement d prime of y1 y2. See, d prime of y1 y2 is equal to d of f inverse of y1 comma f inverse of y2. But we know that d is a metric actually on x, so the distance between any 2 points on the space x, because these 2 points are the points on x, which are the inverse images of the points y1 and y2, which exist in y. So the distance between these 2 points will be a positive quantity or equal to 0. So this quantity is greater than or equal to 0. First condition is thus is verified. Next, second condition. Here we want to show that d prime of y1 y2 equal to d prime of y2 y1. That means the position of the elements or the members of y here we have chosen is not a serious thing. You can reward the position of the points y1 and y2. So for that that will be proved next. Here we are going to show, we can show that the position is not important. Here we show that is the third condition actually. So d prime of y1 y2 equal to then d of f1 inverse comma f2 inverse. But using the condition, using the third condition for the metric d, we can rewrite this as d of f inverse of y2 comma f inverse of y1. Here actually we interchange the these two elements, and thus we get that this is equal to d of f inverse of y2 and f comma f inverse of y1, and we get that it is equal to d prime of y2 y1. That means the position of the members present in the function d prime does not affect its value. That means the third condition is satisfied. Next, coming to the second condition, we want to show that d prime of y1 y2 equal to 0 if and only if y1 equal to y2. For that, you can expand it as an if and only if statement. It's as an implying and implied by statement. So see, this statement is true if and only if d of f inverse of y1 comma f inverse of y2 equal to 0, and that happens only if f inverse of y1 equal to f inverse of y2, and that means it's equal to if and only if y1 equal to y2. So this can happen. The distance between y1 and y2 can be equal to 0 if and only if y1 equal to 0. That means for two different points, the distance between the 2 points is not a quantity which is equal to 0. Thus the second condition is verified. Now to verify the third condition, you know that we need 3 points. Actually the third point, the first 2 points are y1 and y2, which belong to y. A third point is also required, but that point is not appearing here in the in this part, but and the third point is there, y3. So we consider y1 y2 and y3 the 3 points which are members of y, and then you can, related to these 3 points which exist in y, we can think about its inverse images, f inverse of y1, f inverse of y2 and f inverse of y3. Where are these 3 elements present? And they are present in the first space x. And then we write d prime of y1 y2, d prime of y1 y2 equal to, then converting it, this cannot be d prime here, it must be corrected. So it's d of it's d only of y1 comma f inverse of y2. But now comes into picture the third point, comes into picture. By using the third point in the inverse image of the third point, that's f inverse of y3, you can split this quantity as the sum of 2 terms, and due to this, this equality symbol then is then changed to less than or equal to an inequality symbol. Thus this equality becomes less than or equal to, and we get that it is d of f inverse of y1 comma f inverse of y3 and plus d of f inverse of y3 comma f inverse of y2. See, d of f inverse of y3 d f inverse of y2. So see, these mistakes must be corrected. This symbol should be this at three places these symbols should be, and yeah, at three places the symbols are wrongly written. But this can be reconverted into in the form of the second metric d prime. So using the definition, thus we can write here at this place you can write d prime of y1 y3 y1 y3 see this, and plus d prime of y3 y2. See, y3 and y2 are the points, and actually these numbers are not coming from the air, and they are actually related to these y1 y3 and y1 y2 and y3. All these are related to these points. See, thus we get that the fourth condition is also satisfied for d prime to become a metric on the space y, and therefore we conclude that d prime is a metric actually on y. Next we proceeded to prove, we want to prove that this metric d prime, the metric d prime which is on y, can generate the topology on y, because already y is a topological space. It is given as a topological space, so there exists a topology of y. Already there exists open sets, and these open sets are present in the topology. Okay, but they are independently actually defined. The open sets are chosen independently, and they are collected in the topology to define the topology on y. But here in this situation, we want to show that that topology can be generated by the metric, the new metric d prime, which exists, which is proved as a we have proved that this is a metric on y, and that new metric d prime can actually determine the open sets on open sets of the topology that exists on y, and that's our aim in the next few steps. Okay, so we proceed with we start with the open set, arbitrarily choose an open set of open subset of open set of y. That means O is an element of the topology. So O is a member of the topology, existing topology O on y. Now we proceed to prove that O is the union of we need only to prove that O, this set O, open set O, is the union of open balls, a collection of open balls. So union of open balls generated by which are generated by d prime. See, metric can generate open balls. So we want to show that the open set can be written as the union of open balls which are generated by d prime. So for that let's choose a point of O. Y be an element of O. We choose an arbitrary point of O. Then we will show that this Y there exists we will show that there exists an open ball. See, we have chosen Y an element of the open set, and next we will show that there exists an open ball in the space Y. There is an open ball in the space Y which contains the element Y. The element Y is contained in that open ball, and that open ball is a subset of the open set chosen. So that is the thing that we actually want to show. But see here, f inverse of y, you can think about f inverse of y, since y is an element of the open set, and now we think about f inverse of y. F inverse of y is an element of f inverse of O. You can take the inverse image of open set. It is now present in X. So f inverse of O is a subset of X, and surely we get that f inverse of y is a subset of f inverse of O. It's because y is an element of O, and since f is 1 to 1 and 1 to, all these makes it sure that f inverse of y is an element of f inverse of O. Since f inverse of O is open, but we know that f inverse of O is open in X. Why? Because O is an open set in Y, and f inverse is an open mapping. F inverse is an open mapping. So we get that f inverse of O is an open set in X, and therefore there exists we can choose an R greater than 0, a positive real number R greater than 0, such that at this moment we can choose an R greater than 0, such that the open ball, see B is the open ball here. B with respect to that the metric D. With respect to the metric D, we choose an open ball B D of f inverse about the center, about the point f inverse of y. Why here f inverse of y acts as the center of the ball which is chosen. So f inverse of y comma radius is specified here. So then that can be used here at this price. So comma r it is closed, so which is such that so BD of f inverse of y r, it's an open ball, is a subset of f inverse of O. Yeah, and then clearly if you apply f on both sides of this expression, we get f of BD of f inverse y of r is a subset of O. Because applying f here, it nullifies the effect of f inverse, and we get that it's equal to O, and thus this set is here we obtain a set, and that set is subset of O. Now we will prove that B D prime, see B D prime, remember that then this is an open ball. It's a B stands for an open ball. This open ball B is in it's a subset of the space Y, or it is in the space Y. So BD of YR is then see BD prime. Okay, then we want to show that BD prime of Y comma R is a subset of O. So let A be an element of for that we choose an element A, an arbitrary element. We choose any point of the open ball. So let A be an element of the open ball. We have specified here that open ball B D prime of YR. Then since A is an element of that open ball, and the radius of the open ball is R, and its center is equal to Y, we can write very easily, we can write that D prime of Y comma A comma Y is less than R. Why? It's because the radius of the open ball is R, and Y is the center, and A be any point of the open ball. So A can be equal to Y also. If A is equal to Y, then we get 0. If A is equal to Y, what happens? Then the distance between A and Y will be then equal to 0. So that situation, that value will be equal to 0. Then that situation also is possible. It can be then correct also. It's because 0 is less than R in that case. So when Y is equal to R. Anyway, A is an arbitrarily chosen element of that open ball, and therefore D prime of A, that is the distance from the point A to Y, is therefore less than R. Why? It's because R is the radius of the open ball, which is defined here. Then then D of f inverse of we can now think about the inverse images of A and Y, and that is happening in X. So you take the points f inverse A and f inverse of Y, and the distance between the points f inverse of A and f inverse of Y, that is distance between f inverse A and f inverse of Y, will be then less than R. Why? It's because we define that D prime of AY is equal to D of f inverse of A and f inverse of B. Clearly f inverse A and f inverse B for this element, for this candidate, for this member of this open ball, that exists f inverse, and we get that D of f inverse of A comma f inverse of Y is less than R. Why? It's because we have defined that D is equal to D prime, or the distance between the 2 points, between any 2 points in X is equal to distance between the corresponding images of the points that exist on the second space. So that means the matrix actually that gives the same value for any 2 points and its image points. So using that we get the D of f inverse of A comma f inverse of Y is less than R, and therefore clearly this states that f of A is an element of thus f A is an element of BD of f inverse of Y, f inverse of I comma r. So see how do we get this fa, and it's implied by this statement and by this fact. Okay, now f of a, therefore due to this, why it's because the distance, this says that the distance from the point f inverse of a to f inverse of y is always less than r, where r is the radius of the ball that we choose here. R is the radius of the ball, as we have chosen. See, r is chosen such that the radius of r is greater than 0 is chosen such that BD of f inverse of y comma r is a subset of f inverse of r, and r is the radius of this ball. Okay, now we get that f of a is an element of BD. F is an element of BD of f inverse of y and r, and therefore by then removing the function f, and we get that thus a is an element of f of, thus we get that a is an element of f of BD, f of BD of f inverse of y and f inverse of y r, and it's a subset of O. See, therefore so a is chosen here. Now we have a correction here, because a is an element of BD prime of YR actually. Okay, so let's come back. Thus we get that this is a is an element of the second space. So that means we have to choose f inverse of a. See, here we have to choose f inverse of a. This f inverse of a is a member of is an element of BD of f inverse of YR. So this happens in the space of X, in the first space. Okay, in the first space f inverse of a. So you have to choose here, you have to write f inverse of a. F inverse of a is an element of BD of f inverse of y comma r. That means the distance from the point fa, f inverse of a, distance from the point f inverse a to the center f inverse of y of the ball is always less than or equal to r, or more clearly it is less than r. And this shows that a is an element of f of BD f inverse of a, f of BD f inverse of y. See, therefore by applying, since we have f inverse, then we apply f on both sides. Thus by removing f, we have already this must be corrected, this statement must be corrected. Here you have to put a minus on f inverse, actually this function. So f inverse of a, and then after getting this, you can apply f on both sides. So f of f inverse of a makes this quantity, this value equal to a. Thus a is an element of then you have to write f of BD of f inverse of YR. It's a subset of O, and that means a is an element of O. Thus by choosing, since we have chosen an element of the open ball, it's an arbitrarily chosen element of the open ball, and that point, that chosen point, arbitrarily chosen point, is obtained an element of O. And therefore what we can conclude that this open ball, the open ball which exists here, and BD prime of YR, that open ball is completely present in the open set O. So that is the conclusion of the previous steps, of these steps, and therefore we get that we get that the open set O can be written as the union of see here by writing this, by A is an element of, or by obtaining A is an element of O, we can conclude that A is a member of the open ball. It's arbitrarily chosen, and hence since in the last step you obtain that A is a member of O, that means every element of that open set, open ball, every element of this open ball is a member of O, and therefore this open ball B D prime of YR is a subset of O. So this is the statement that we have proved, even though it is not written here in the last step. Here somewhere after this stage, after this line, you should write that also. We obtain that BD prime of YR is a subset of O. This is what we proved there. Okay. And then after proving that this open ball is a subset of O, we get that O can be written as the union of open balls, and therefore finally we can conclude that the topology on the space Y is actually generated by the second metric D prime, which we have proved that it's a metric on the second space, and this D prime can generate the topology on Y, and that means Y is also metrizable. So whenever X is metrizable and X is homomorphic to a second space Y, then that space Y is also metrizable. Okay, that is the final conclusion of this discussion. Okay, thank you.